Welcome to pre-calculus video for skill number 36. I can identify key features of power and polynomial functions. And featured here we have a backpack, and this backpack is called a top loader, and we know that because we have this lid which can be opened up and contents can be put into the backpack from the top. So there are two kinds of backpacks, a top loader, and the trivia question is, what is the other type of backpack? Alright, before we start working through the homework, I wanted to talk about a few key things about power and polynomial functions. So a power function is anything that is x raised to some number, some whole number, some integer. So we could have x to the third or x to the fifth, or even x to the 110th. We can also stick a number in front of it, maybe 3 or 7 or 21, any positive or negative number. These all have terms. The whole thing is called a term. The number in front is called a coefficient. And the power is called the degree. So you'll hear me throw these words out several times. A power function is anything that has a single term, 7x to the 75th. So that's a degree 75 with a leading coefficient of 7. And this is a power function. If we take a couple power functions, or more than two, and add them together, for example 3x to the 21st minus 7x to the 3rd, then what we get is a polynomial. So you'll hear me use those terms pretty regularly. This chapter is, or this unit, focuses on polynomial functions. So before I jump to the homework, let's do one more quick thing. Polynomial functions, regardless of how many terms they have similar end behavior. So let's just 5x to the 6 minus 4x to the 8th. Let's not do 8. Let's do 4x to the 3rd and 2x to the 1st. The degree of the highest degree of the polynomial tells us a little bit about end behavior. So if it is an even degree, both ends are going to point in the same direction, either up or down. And what goes on in the middle is may vary a little bit, but the end, it happens the same. And an odd one goes up and one goes down, and what happens in the middle varies. So what we have here is we actually have a table that we're creating, which is useful for understanding behavior. So if you have an even degree or an odd degree, this would be a positive leading coefficient, and this is a negative leading coefficient. So what we have here is this whole polynomial starts out with a positive leading coefficient and an odd degree. So a positive leading coefficient and an odd degree. So the polynomial will look something like this. And this sort of table here leads us into our first problems from our problem set. So let's take a look at those. Alright, so the first questions we have are identifying the long-run behavior of the function. And so what that's doing is asking us to kind of understand what's going on. I see that this power function has a degree of 6 so that it's even. So they either both go up or they both go down, the graph of it. And the leading coefficient is positive. So I know that they both go up, both ends. So what I could say is as x goes to infinity, f of x goes to infinity as well. And what that's saying is as we go to the right, the function is going up. And then we can also describe what's going on as x goes to negative infinity. As x goes to negative infinity, so as we go to the left, our function also goes up. So as we go leftward, our function is going up. As opposed to example 5 where we have a odd degree. So our odd degree tells us that one goes up and one goes down. Our leading coefficient is also positive, positive 1. So I know that the function looks something like this with some weird thing going on in the middle perhaps. So again, as we move to the right, we go up. So we'd say as x goes to infinity, f of x is going to go up, or also goes to infinity. And as we go to the left, our function is going down. So we write as x goes to negative infinity, f of x goes to negative infinity. So problems 5, 6, 7, and 8 are very similar. I'm just going to do problem 8 for you. What we have is a odd degree, so they go in opposite directions, and a negative leading coefficient. So they go opposite directions, and the negative leading coefficient tells us that we have a general downward trend. So it kind of looks like that. And our answers will be as x goes to infinity, f of x is going to go to negative infinity. See how as we go to the right, the function is decreasing. And then as x goes to negative infinity, our function is actually going to go to positive infinity. So as we move to the left, the function is going upwards. So this end behavior is nothing new to us. So let's take a look at some of the other questions that we get. Identify the degree and the leading coefficient of each polynomial. Well, this is pretty straightforward. The degree is the highest number of the exponents. So in this case, we only have one exponent, so our degree is 6. In problem number 12, we have 3 terms, but the highest one is the 3, so our degree is 3 there. In problem 14, we have 1, 2, 3, 4 terms, but our highest one is a 5, so our degree is 5. And if you look at problem 16, we actually don't have it in the kind of standard form. It's actually in a factored form. So off to the side, we would probably want to distribute our factors. So I'll combine those two, and I'll have 3x squared plus 3x plus x, so that's plus 4x plus 1, and I want to multiply that by 4x plus 3. And you'll find that the only thing that matters for degree and leading coefficient is going to be the highest terms, and when we multiply those together we get 12x to the third. We can go ahead and figure out what the rest of the terms are, but it's not necessary for this question. So the degree we have here is 3. You might notice that we also have 3 terms, 1, 2, 3, and none of those terms are squared, so our degree stays at 3. The leading coefficient, our leading coefficient is the number in front of the power. So we've got 5x to the 6th, So our leading coefficient in this case is 5. In this case, our leading coefficient is -4. In this case, our leading coefficient is 6. Again, on problem number 16, we'd multiply it all out, and we see that our leading coefficient is 12. Okay, let's take a look at the second page. Again, we're looking at long-run behavior of the function, and the great thing about identifying long-run behavior of a polynomial is all we care about is the highest degree, so this term. The rest of these don't matter in explaining long-run behavior. And so for this function, the degree is odd, so I know it goes in opposite directions, and the leading coefficient is positive, so it generally does something like this, and maybe it does something weird in the middle. But the end behavior is the same, so as x goes to infinity, f of x also goes to infinity. So as we go to the right, our function increases, and as x goes to -infinity, our function goes to -infinity as well. So there we go. As we go to the left, our function is decreasing. And if you're having trouble picturing what this graph might look like, go ahead and type it into your grapher and see what it does. So I'm going to leave the remaining 3 ones to you because it's kind of a straightforward problem and very similar to the last ones. Problem 21. What is the maximum number of x-intercepts and turning points a polynomial for degree 5? So the interesting thing is a degree tells us how many times we can cross the x-axis, a maximum. So a degree 5 at most will cross the axis 5 times, which means maybe the function looks like that. It doesn't have to cross 5 times, but at most it will cross 5 times. So the maximum number of x-intercepts is 5, and the turning points is basically how many times did we turn directions. So we turned once, twice, 3 times, and 4 times. So the number of turning points is 4. And your maximum number of turning points will always be 1 less than the degree. So, oops, I did 21. I guess 22 you'll need to do on your own. I should have done the even problem. Sorry. We can extend that knowledge by looking at the graphs below, and it says what is the least possible degree for the polynomial function. So here on 24 we have 2 intercepts, so at a bare minimum our degree is 2. It could be more than that, but at a bare minimum it has to be at least 2. Looking at 26, we have only 1 crossing point, so at a bare minimum our degree would be 1. On problem 28, we see that it crosses twice. However, we also have more than 1 turning point. So our turning points, we have 1 turning point, 2 turning points, and then 3 turning points. And so that's more informative to us that if there's 3 turning points, then a bare minimum degree would be 1 more than that. So a degree of 4. And we can apply that to problem number 27 and 29. Problem 30, we have no intercepts, so intercepts won't be useful to us, but we do see 1 turning point, so the degree is always 1 higher than the number of turning points, so our degree has to be at least a 2. Alright, looking further down, we are asked to find the horizontal and vertical intercepts for each function. So a horizontal intercept occurs if you're thinking about this graphically, it's where the graph touches the axis or crosses the x-axis. So horizontal intercept occurs when the function is equal to 0. So if we set our function, in this case f of x, equal to 0, we can apply the zero product property and find out that this occurs. We have three instances, one at when x is -1, one when x is 4, and one when x is -5. So our horizontal intercepts occur at those three locations: -1, 0, 4, 0, and -5, 0. And to find our vertical intercepts, those happen when x is 0. So if we stick our 0 in for x, we're going to get 3 times 0 plus 1, 0 minus 4, and 0 plus 5. And that will occur at 3 times 5 is 15 times -4, -60. So we get it at -60. So our vertical intercept occurs at 0, -60. And we could use this information to draw a rough graph of the function if we wished. Here we have a crossing at -60, and then we also cross at -1, -5, and 4. And so we have some sort of function which probably does something kind of like that. And we'll get into graphing it more later, so don't worry about that aspect. Right now we're just identifying the intercepts. We apply the same approach for number 34, and we would find that there is a horizontal intercept at 4 and one at -3/4. So horizontal intercept at 4, 0, and one at -3/4, 0. And our vertical intercept is going to occur at 0, if we take the values, we get -3 times 4 times 3, -9, that's -36. Alright, and we'll go over this more in class, but this is, I hope, a straightforward skill for you. The skill test is actually, I used the exact phrasings of all of these questions, so this assignment should be a perfect model of the skill test. Please bring your questions to class, maybe write them off to the side, and we'll talk about things in class. Alright, have a good day. Oh, the last page. Alright, after this I hope that you understand key features of power and polynomial functions. Remember, a power function is just one term, like 3x squared, whereas a polynomial function is a collection of power functions. The key vocab here is this is a power function of degree 2. This one is a power function of degree 7 because that's the highest degree. The leading coefficient of this one is 3, and the leading coefficient of this one is -5. So you got to write it in standard form before identifying the leading coefficient. And you should be able to identify end behavior of these two functions. The end behavior of 3x squared is both ends are going upwards, and the end behavior of this trinomial, this polynomial of 3 terms, is the left side goes up and the right side goes down. Anyway, the answer to the trivia question, we have the top loading backpack, and then there is also a panel loader. which basically consists of lots of different pouches on the inside or on the outside that you can load content into. Oftentimes our panel loaders also have a top load location. Alright, thanks for watching the video.